Cool, so all we've got now is just part 4, which is more kind of qualitative, more kind of description and understanding your, well, understanding your understanding really, making sure you know what you're talking about. It's to do with making it more realistic, adding a damping term. Now I'm going to pick the box on the spring example from the last 3 we did in part 3. For me it's the easiest one to visualise, it's the kind of one I can kind of see the most, if you see what I mean. It's easy to visualise. The LC circuit, I really struggle to visualise that one, and the pendulum, you've got that mixture of displacement and angle, which makes it a bit harder to really grasp. Yes, we've got this system. Now earlier, we described this system, we took the box out and we said there's only one force acting on it. It's a frictionless table, we're not going to consider gravity or anything, so there's one force going that way, which is Kx. Okay, we make this more realistic, we add a damping term, we add another force, which is friction. Now friction is proportional to the velocity it's travelling, okay? And it also makes sense, hopefully intuitively, that it's proportional to negative the velocity. If it wasn't, your car would just speed up kind of perpetually. Whereas we know if you take your foot off the accelerator, friction will cause the velocity to slow down. It will cause the velocity to decrease, it'll decelerate, so the friction acts the opposite to velocity and proportional to it. So the faster you go, the bigger the friction. So we're adding another force in here going backwards. The velocity is going left to right, so the friction is going from right to left. We know it's proportional to velocity, so I'll add a proportionality constant in there, which we'll just call C for now. So F total equals minus Kx, because we're going right to left, minus Cv, because we're going right to left. And what we're going to do is going to make F equal ma minus Kx minus Cv. Now, as we know, acceleration is the double derivative of displacement, and velocity is the single derivative of displacement. So let's pop those in. You have mx double dot equals minus Kx minus Cx dot. Drag them all over to the left-hand side. So that's 1 dot there, that's 2 dots there, plus Kx equals 0. And this is our new equation. So the damping term comes from a damping force on the system, which is directly proportional to the velocity of the system, but in the opposite direction. And I think that's really all they want from that equation there. From the question there. Try it out for the pendulum, and also try it out for the LC circuit. Obviously you need to add a resistor in there for the damping term, but hopefully that should be pretty self-explanatory. There's a friction of force, or there's a resistance of force, which is proportional to the velocity and in a negative direction. Great, that's A1 done. I'll see you for A2.